Hello. Today we are going to look at the synthetic addition polymer. We're going to cover the following areas. Start from the definition, general formula. I will also talk about the functional groups, nomenclature, the physical properties, the reactions, as well as the creation of synthetic addition polymers. Then I will briefly introduce you the uses and molecular models. Okay, so what are polymers and what are synthetic addition polymers? A polymer is a very long organic compound comprised of smaller base compounds linked together. The smaller base compound is referred to as a monomer. The synthetic addition polymers are the simplest type of polymers. They are generally man-made substances with a high strength and durability while retaining their flexibility. Addition polymer is a polymer that forms by simple linking of monomers without the cogeneration of other products. Addition polymerization differs from condensation polymerization, which does cogenerate a product, usually water. They make up many substances today, including PE, PVC, and styrofoam, PTFE, also known as Teflon, etc. So what is the general formula of synthetic addition polymer? We know that the presence of a double bond is needed for monomers to link together and form a polymer. And these monomers react together to form a larger compound. For example, when two ethanes react, they split their double bonds to form a polymer, and more ethane monomers react with the polymer, and the chain continues to grow. So for example, the formula for polyethylene is C2H4 bracket N. N simply means many. It can be hundreds, thousands, or hundreds of thousands in reality. Functional groups. Polymers are made up of base, hydrocarbons, and any functional groups they attach. The base structure of a synthetic addition polymer consists of the base monomer repeatedly linked together to form a long hydrocarbon chain. Any functional groups present in the monomer will be carried over to the polymer, along with the properties associated with them. Now let's look at the nomenclature. Nomenclature means the system of names. And the naming of polymer is very simple. So you first take the IUPAC name of the monomer, for example, ethane, and then you add the prefix poly, become polyethane. Poly means many. In terms of how to draw the polymers, first you draw the Lewis structure of the base monomer, then you place the brackets around the structure with bounds to show where it links into the polymer chain. A subscript is used to denote the number of monomers within the chain. In most cases, the number of monomers is unknown, so you put an N as a placeholder. For example, the one on the left is the Lewis structure for vinyl chloride. And when this monomer polymerizes, it becomes polyvinyl chloride. You put a bracket, you open the double bond, make it become a single bond, and then you put an N outside the bracket. The physical properties. Synthetic addition polymers make up things like polyethylene, PE, polyvinyl chloride, PVC, PTFE, like Teflon. Polymers form very long chains and often networks similar to ionic salt bonds. However, unlike the ionic bonds in salt crystals, the forces between organic compounds are largely van der Waals forces. This makes these polymers very flexible while retaining their strengths. Polymers also tend to take on the characteristics of the functional groups attached to their monomers. Take PVC for example. It is very waterproof, and this is due to the large repulsive forces that come from the large electronegativity of the chloride group. Now let's look at the polymer reaction. So first you have the polymerization. During a polymerization reaction, the double bonds in the monomers split, and the electrons are used to bond the monomers together. One electron remains and is used to continue bonding with other monomers. And the inverse process can also occur, which is also known as depolymerization, for example, during the digestion of food. However, this process can produce either the same base monomer that originally formed the polymer or a mix of different hydrocarbons of various sizes. We also have cross-linking polymers. Polymer chain can be strengthened, cross-linking between the chains to form a lattice-like structure. It's like the molecule bridges between these polymer chains. For example, the PEX pipes, which is the cross-linked ethylene. It is super extra strong because of those cross-links. The creation of polymers. There are 3 stages of polymer creation: the initiation, propagation, and termination. In the initiation stage, the polymerization process begins when 2 monomers encounter. A double bond in each hydrocarbon splits, with one electron forming a bond between the 2 monomers and the other being left over. Because a double bond is required, so remember that alkanes cannot polymerize. Then in the propagation stage, as the forming polymer encounters another monomer, the leftover electron forms a bond with the monomer, and the double bond of that hydrocarbon splits to continue bonding with other encountered monomer. Then the termination stage. The polymer chain will continue to get larger, often until it numbers in thousands or millions of monomers long. The reaction will continue until it encounters another forming polymer. The extra electrons from both polymers will pair up and stabilize to form one polymer chain. Because there is no more electrons, the reaction will not continue and the polymer is formed. Now let's look at the uses of the polymers. Synthetic addition polymers are useful with their high strength and durability while retaining their flexibility. Some examples of synthetic addition polymers include, for example, polyethylene, PE, being the most popular plastic. This is the polymer that makes grocery bags, shampoo bottles, children's toys, and even bulletproof vests. Another fantastic feature of PE is that they are thermoplastic, meaning it can be melted and reformed, making it recyclable. PVC, the polyvinyl chloride, is a common plastic used for plumbing pipes. It is very light, waterproof, and inexpensive to produce. Styrofoam is a polystyrene used to keep packages from being damaged to its lightness and also ability to hold its shape, but it crushes easily under force. Now, PTFE, also known as Teflon, is commonly used as a non-stick coating for pans and other cookware. It can also be used as lubricant. It reduces friction, wear, and energy consumption of machinery. The major application of PTFE, consuming about 50% of the production, is for the insulation of wiring in aerospace and computer applications, like hookup wire, coaxial cables. Now let's look at the molecular models. So first, polyethylene. We already know that the formula is C2H4 bracket N. So as you can see, a lot of C2H4 linked together. Then polystyrene. This is the styrofoam. This guy is the PTFE. Teflon is the polytetrafluoroethylene. Please note that comparing to C2H4 bracket N, polyethylene, this Teflon monomer is C2F4. So hydrogen, all the 4 hydrogen have been replaced by fluorine. As you know that fluorine is the most electronegative in the periodic table, and fluorine loves electrons because it holds onto its electrons so tightly, and it is so satisfied in this polymerized chain. The electrons are unavailable for even minimal interaction with any other molecules. Here, I'm not just saying the stuff is super difficult to react with, or it's really stable. It's more than that. The electrons aren't even available for the sort of interactions that make things stick to each other or cause friction. This is why Teflon is super useful. Next are Nomex and Kevlar. As you can see, these two, the molecular model are quite similar. Okay, by now, we have covered the definition, general formula, functional groups, nomenclature, how to create polymers, the uses of polymers, and their molecular models. Hope you get some basic idea of what a synthetic addition polymer is. If you are interested in it, or if you have any questions, you are more than welcome to send me an email. Thank you.